So hello students, welcome to the second lecture of this series where we are doing revision of essential class 11th physics. So in the first lecture we had discussed some basics about vectors, and we will be continuing with vector analysis in today's session. So if this is the first session you are attending, then I would urge you to also go through the video of the first session which was earlier in the week, and go through the video of that session, and you will be better able to follow and understand what's happening in today's session then. So this is part of a series we are doing where we are doing some revision of essential parts of vector analysis and basic calculus for physics. Okay, so let's look at this now. So we'll pick up from where we left off directly in the last session, which was we were discussing about the parallelogram law of vector addition and subtraction. So let's quickly go through that part again. So parallelogram law or parallelogram theorem, whatever, is something that applies to addition and finally simultaneously subtraction within the same principle or within the same geometrical shape. We can see both the addition and subtraction of vectors. However, we are limited to dealing with two vectors at a time in this. Very soon we will be coming to addition of multiple vectors also. So here we are dealing with vectors in geometrical form. So parallelogram law is like this, that suppose we have one given vector A like this, represented by this vector arrow, and a second vector B represented by this vector arrow. And we know the magnitude of the vector A, that is a given quantity, the magnitude of the vector B, which is a given quantity. Remember that when we are adding or subtracting, it means that vectors A and B have to be of the same physical quantity, and they have to be expressed in the same units. That's of course understood here. And we know theta, that is the angle between vectors A and B. Okay. So in this diagram, you can see that A's direction is along this axis, okay, and B's direction is along this axis. So the angle theta we are talking about is this angle theta, the angle between the two axes, the line of action of vector A and line of action of vector B. So that is the angle theta we are talking about. Okay. So how we set up the parallelogram law is that you draw a vector parallelogram for which there is this series of steps. Okay. The first step is that you draw the vector A and B respectively from a common origin. So remember, these vector arrows are movable. So from some common point as the origin of both the vectors, you draw vector A first, and you draw vector B such that the angle between them is whatever theta we know it to be. That is this angle theta between the two vectors. And this vector is an arrow of the given length, which is the magnitude. And this vector is another arrow of the given length, which is the magnitude of B. Next up, what we do is we complete the vector parallelogram by drawing two parallel sides, two adjacent parallel sides. So opposite to A, we draw a side parallel to A. Opposite to B, we draw another side parallel to B. So that gives us the shape which we call the vector parallelogram of A and B. Now within this shape, we see that the primary diagonal, that is the diagonal drawn from the common origin to the opposite vertex, that becomes our vector sum. That becomes what we call the sum or the resultant of A and B. And the angle that this makes with A, we can denote with the symbol alpha. Whereas we can see the secondary diagonal, which is basically the diagonal from the head of one of the vectors to the head of the other vector, that becomes the difference. So for example, if the arrow is pointing from B to A, from B's head to A's head, then it becomes A minus B. Whereas if this diagonal arrow, I was pointing the arrowhead from A towards B, then it would have been B minus, it would have been A minus B. So remember, if it is B to A, it is A minus B. If it is A to B, then it is B minus A. And this angle is beta. Okay. So once we are familiar with this diagram, we will see that a lot of properties of vector algebra and a lot of special cases, etc., shortcut formula, etc., can be developed from this. Okay. However, the fundamental formula, of course, which apply to this situation, let's take a look at those also. Okay. So those fundamental formulae. So just coming back here for a moment, the first thing you have to understand is that given two vectors in geometrical form, A and B are known to us in geometrical form. That means we can draw them as arrows. We know the length of the two arrows and we know the angle between them. How can we construct the vector parallelogram? So the step for constructing the vector parallelogram is first you draw the vectors A and B from the common origin, as I've done here. From this common origin, I've drawn the two vectors A and B. Then I complete the parallelogram by drawing the other two parallel sides. And once I complete the parallelogram, I can understand that the diagonal which is from the origin to the opposite side, that becomes the sum of the two vectors. And the diagonal which is from head of one vector to head of the second vector, that becomes the difference. So if it is from B to A, then it becomes A minus B. If it was opposite to this, then it would have been B minus A. Okay. Now the next step in this is that we want to understand the formulae, which we have seen already. The formulae for finding out the magnitude and direction of the vectors, that is common to the triangle law, which we had seen earlier. So let's quickly go over those formulae once more. So given the magnitude of A and B and the angle theta, so those quantities being known, now the important formula becomes that for the sum of the two vectors, we have magnitude of A plus B, or magnitude of the resultant sum of A and B, as you know, is given by the triangle law formula, which is common to the parallelogram law. Okay. And the angle alpha is given by the formula tan inverse of B sine theta upon A plus B cos theta. Whereas for the difference of the two vectors, you can see that this is given by the formula square root of A square plus B square minus 2AB cos theta. And the angle beta is given by tan inverse of B sine theta upon A minus B cos theta. So this is same thing as the triangle laws that we had learned in the first session about, or rather we had revised about in the first session. Remember, these are basically a series of revision lectures. If you are new to vector algebra, then I would suggest that you first go through some reference material and pay more attention to the basics, and then come back to these revision lectures, which are more about the applications than the basics. Okay. So now, what is the main purpose of parallelogram law? It is to make certain properties of vectors very easy to understand, and certain relationships between vectors in context of sum and difference. It makes that very easy to pick up, okay? Because it's visually a very simple diagram, a parallelogram, and more importantly, within the same diagram, we get to compare the sum and difference. Now, both the diagonals, we can visually compare them and understand from the properties of the given parallelogram what is the relationship between the sum and the difference. So that is the main use of the parallelogram law. Okay. The other thing is that it also makes it easy to understand visually something like the addition of forces. For example, what I'm saying is that if you have a situation later in physics where we are applying vectors in something like, let's say, Newton's laws of motion. So on a body, suppose we are applying some external forces. Okay, so let's say this is a body which is on a smooth horizontal surface, and we are seeing this from top, and we are applying two forces on it, F1 and F2. Now we want to understand what will be the direction of its acceleration. So it's visually very easy to understand that if these two forces are acting on it, and we have that the net force is the vector sum of F1 plus F2. And then we go on to apply Newton's second law, that the net force on this particular body of mass m would be equal to mass into acceleration. So now it's visually very easy to understand from parallelogram law that the resultant of these two forces would be this diagonal. We have to just construct this parallelogram, and then we have to understand that the diagonal of this parallelogram would represent the net force. So it's visually very easy to understand from this that therefore the body will tend to accelerate in this sort of direction. Okay. Because whatever is the direction of the net force, same has to be the direction of acceleration. So it will accelerate along this line. So that again is something which makes the application of parallelogram law a very natural process for things like Newton's laws of motion further on and things like that. So again, it's a very useful thing. Okay. But coming back, we'll come back to all those things later. Now let's concentrate on some properties of vectors in context of sum and difference using the parallelogram law. And we'll see a lot of examples where you'll see that at your JEE level or your competitive exam level, how you can sort of apply some shortcut methods to typical type of questions which involve sum and difference of vectors. So first thing we'll see is that if you compare a situation where the angle between two vectors is 90 degrees, another situation where the angle between two vectors is greater than 90 degrees, less than equal to 180 degrees, and compare it with a situation where the angle is acute, less than 90 degrees, greater than 0. If we compare these three situations in terms of the parallelogram, so you immediately come to this very important conclusion that here suppose A and B are like this. Here we are dealing with a situation where the same two vectors are at an are at an obtuse angle, whereas in this case taking the same two vectors but they are at an acute angle. So we are visually comparing these three situations. So you will immediately understand that the diagram in the middle is a special type of parallelogram, which is the rectangle. So we will make use of the special properties of rectangle which we know. And for example, one of the properties is that the two diagonals are equal in length. Another property is that both the diagonals are at same kind of angles with respect to the sides. So those properties that we are familiar with at the geometrical level, now we will see how that will help us to understand vectors better. Okay, so this is a very key thing in understanding vector algebra, and it becomes very important in our physics applications later, because just by visualizing this kind of figure now, we can understand the relationship between things like two force vectors or two field vectors or something very fast in a given problem. It helps us analyze things a lot. Okay, so what is the property of rectangle? The property of rectangle is that the diagonals are of equal length. So that immediately now applies to the sum and difference. So here this will be the sum. Here this will be the sum. In each of these, see, this is the resultant. This is this angle. Here this is the resultant. This is this angle alpha. Now if you compare this primary diagonal with the secondary diagonal, which represents the difference of the two vectors, now you start to notice that what is the contrast between the first parallelogram, which has an acute angle on this side, the middle one which has a 90-degree angle, therefore it becomes in fact a rectangle, and the last one which has an acute angle, which has an obtuse angle at this side. Okay. So start to visually understand the difference between these two and how that becomes significant for us in terms of vector algebra. So now let's come to the properties. So we can see that diagonals are of equal length. Okay, because we are dealing with 90 degrees, so this is becoming a rectangle. So what that means in terms of vector algebra, that mod of a plus b becomes equal to mod of a minus b, which becomes equal to square root of a square plus b square when theta is 90 degrees. So this is very important property of vector algebra, that anytime we have this relationship that magnitude of the sum is equal to magnitude of the difference, the only situation possible for that to happen is that theta is equal to 90 degrees. Other than that, of course, if one of the vectors is a null vector, but we are not getting into that. We are assuming that both the vectors a and b have non-zero magnitude. So that is the case. Okay? And the other important property is that this angle alpha is equal to that angle beta, which is equal to tan inverse of b's magnitude divided by a's magnitude. So these two become very important properties which apply in a situation when theta is equal to 90 degrees. Okay. Now, if you were to compare this diagram with this diagram, now just try to understand what's happening. That rectangle has become bent like this into a parallelogram. So when you bend it like this, you can visually see that this diagonal has become longer than this diagonal. So immediately you can see that when theta is acute, what is happening? Theta is acute. So if you think in terms of formula also, the moment that is happening, cos theta is a positive quantity. So cos theta is positive. So even algebraically, it is easy to understand that magnitude of a plus b will become greater than magnitude of a minus b. So whenever this happens, it means that theta must be acute. It cannot be that theta is 90 degrees, or it cannot be that theta is obtuse. Okay. And accordingly, you can see that beta is greater than alpha. In this diagram, you can see, that these angles will be such that beta will be greater than alpha. On the other hand, when you come from the rectangle to this last one, you can see it's bent in this kind of way. Okay, so it's bent in this kind of way means that the primary diagonal a plus b is getting squashed and the secondary diagonal is getting stretched out longer. Or you can understand it in terms of formula that theta is obtuse. So you know that for an obtuse angle, cos theta is negative. For example, cos of 120 degrees is minus half. The cos of 150 degrees is negative of root 3 by 2. The cos of 135 degrees is negative of 1 by root 2. So cos theta is a negative quantity. So accordingly, what will happen here is that mod of a plus b, that is the magnitude of the sum of the two vectors, will become less than the magnitude of the difference. The secondary diagonal is the longer one for theta being obtuse. And you can also see that alpha will become greater than beta. This angle will become greater. So this is the first set of properties that you can understand the relationship between the sum and the difference in context of the angle being obtuse, the angle being acute, or the angle being 90 degrees. And this is something very important later we'll see, especially when it comes to applications. Okay, so let us see a couple of typical type of questions which can MCQ type of questions at competitive exams which can be answered from this. Okay. So for example, we have a situation where we have two forces F1 and F2 are such that magnitude of F1 plus F2 is equal to 25 is equal to magnitude of F1 minus F2 is equal to 25 newtons. And magnitude of F1 is equal to 20 newtons. So from this we want to find out, first of all, the magnitude of the force F2, then the angle theta between F1 and F2, and we want to find out the angle alpha of F1 plus F2 with respect to the direction of F1. These are the various things that we want to find out. Okay. Now you can see here that this type of question becomes very easy to handle if you just think visually. Okay, because what happens is that the moment you visualize this thing, you realize that you're dealing with a situation where you have this, where now F1 plus F2 should be equal in magnitude to F1 minus F2. So this thing that is given to us, this immediately implies in our mind, we think that, okay, the diagonals must be equal in length. Okay, so that immediately tells us that, okay, we are dealing with a rectangle. That's the only big case where it is possible. So once you visualize that, okay, you're dealing with a rectangle, then the solution is over then and there. You just use the geometry of the rectangle and the rest becomes simple enough. So now you have to just visualize this, that you're dealing with this situation, that we have F1, which is of given length 20 newtons, okay, because this information was given to us. We have F2 of some unknown length, okay, but the angle between them is how much? 90 degrees. So you can see straight away we have answered this question, that theta is equal to 90 degrees. Then as far as this is concerned, the sum and difference. Now you can see that these two diagonals will be of same length and they are 25 each. Okay. So now you can just pick up the geometry of this triangle, and from that you can figure out what is this side equal to, and you can find out what is this angle equal to. This angle alpha we need to figure out. Okay, so just pick up that triangle. You can see that this is 25, this is 20, so whatever this F2's magnitude is, that's the same as this. Okay, and this angle is alpha. So now just apply, Pythagoras theorem and you're done. So immediately we understand that, okay, the magnitude of F2 is therefore square root of 25 square minus 20 square, which is 15. So that is done now. So we know that this answer becoming this, okay, and we can find out this angle now from here. Tan alpha is now becoming 15 by 20 or 3 by 4 or 0.75. So alpha is tan inverse of 0.75, which is a well-known angle. It is 37 degrees. So now you have figured out this part also. Okay, so I've taken the time to draw these figures carefully and all that, but the thing is, you can understand that you can actually visualize this the moment you see the question. Okay, the moment you read the data of the question, actually, you can make a mental picture of it and almost immediately understand that you will be dealing with a rectangle with sides 20 and something, so that the diagonal is 25. So know that if the diagonal is 25, the side is 20, the other side has to be 15, because it has to be that 3, 4, 5 type of right angle triangle. Okay. Of course, it takes a bit of practice also. Okay. And I mean, when we're talking in terms of physics, you will not get a direct vectors question in competitive exam. You will get a question where this is applied in some other situation. Like these might be two forces acting on a body and you have to calculate the net force and things like that. So all the more reason you have to be fast at dealing with these kind of steps. It's not just that you have to know your vector algebra, but you should be pretty fast and accurate with it. So that is where this kind of knowing the properties, having these facts at the tips of your fingertips, all this helps a lot. It will boost your ability to score in these type of tests. All right, so that was an application of this property of vectors we were discussing earlier, this particular property. Okay, now we will come to another important type of question. Now, for example, it is given to us that magnitude of the vector A is suppose 10. Magnitude of the vector B is suppose, or let's take something more interesting. The magnitude of the vector A is suppose 24. Okay, and the magnitude of the is 7, and the angle between them, theta, is obtuse. So that means theta is definitely greater than 90 and less than equal to 180 degrees. Then magnitude of A plus B may be, okay, so let us see how we'll understand this. So now see, the moment we look at theta being obtuse, okay, we know that we are visualizing this type of a parallelogram. We're visualizing this type of a parallelogram. So your primary diagonal A plus B is going to be shorter than your secondary diagonal. So immediately you can understand that mod of A plus B will be less than mod of A minus B. In fact, what will happen is that mod of A plus B will be less than square root of A square plus B square. But at the same time, it is greater than the difference of A and B. Because for theta equal to 90 degrees, mod of A plus B would have been equal to square root of A square plus B square. Whereas for theta equal to 180 degrees, mod of A plus B would have been difference of A minus B. So in this case, this is 25, and in this case, this is 17. Okay. So what we can understand here is that because theta is obtuse, so it implies that our mod of a plus b cannot exceed, I mean, cannot exceed or be equal to 25 also. It's less than 25. Okay. And at the same time, it cannot be less than the difference of the two, which is 17. So that rules out this because it cannot be less than 17. That rules out this because it cannot be 25. It rules out this definitely. Okay. Whereas this is within this range. Okay. So again, a question like this, with practice, you'll be able to understand how to solve this very fast. The moment you see that the angle is obtuse, immediately what should come to your mind is this property. Okay. Or this property, depending on whatever is relevant. Okay, so this becomes another important aspect of the application of these kind of properties. All right, let's move on to more interesting properties of sum and difference of two vectors. Now let's take the special case of magnitude of A being equal to magnitude of B, and suppose that is equal to some A. Okay. Then in such a situation, what happens is that our vector parallelogram will again become a special kind of shape. And yes, you might have guessed correctly, that special shape it will become will be a rhombus. Okay. So depending on whether we are dealing with a rhombus with an acute angle between the vectors A and B, okay, or we might be dealing with a rhombus with an obtuse angle between the vectors A and B. But in either case, the shape will be like this. Okay, this side is equal to this side, equal to A. It's an acute angle, and again this side is equal to this side. This is an obtuse angle. So when we complete this figure of the parallelogram, right, you can understand that we will be dealing with the special type of parallelogram, which is a rhombus. Now start thinking, what are the special properties of rhombus that you know about? Okay. And you'll see how those properties will relate to our vector algebra here. Okay. So I hope you would have guessed by now that one of the important properties of the rhombus is that the diagonals are perpendicular to each other. Okay. And the other important property is that the diagonals also bisect each other as angular bisectors. I mean, they are perpendicular bisectors of each other, and they are also angular bisectors of each other, or rather angular bisectors of the sides. So that will become another important property here. So now because of this, what is happening? Because of this property, our parallelogram, in either case, whether theta is acute or theta is obtuse, it is becoming a rhombus. Now the rhombus has these important properties that first of all, the diagonals are perpendicular bisectors of each other. So that also means that, here this side will be equal to this side because they bisect each other. And here this side will be equal to this side. Right. So the rhombus has these important properties that the diagonals bisect each other perpendicularly. And also the diagonals are angular bisectors of the sides. So that property, now let's understand what that means over here. That property in terms of this means that this angle will be equal to this angle. And it means that this angle will be equal to this angle. These two angles will be the same. So let's understand in context of vector algebra now what these things mean. So in context of vector algebra, it means that first of all, the vector a plus b is perpendicular to the vector a minus b. That's the first thing it means. Okay. Then secondly, it means that the angle alpha is equal to theta by 2, where alpha is the angle of a plus b with respect to vector e. And third, we can reduce this to a shortcut formula that magnitude of a plus b will become 2a cos theta by 2. I will explain to you how this comes also. And magnitude of a minus b will become 2a sin theta by 2. Now this is a particularly useful set of formulae as a shortcut whenever mod A is equal to mod B. So we'll discuss about this also. Okay, how this comes. Just familiarize yourself with this for a moment. Then we'll discuss how the third set of formulae come also. Okay, so now let's understand how we come to this third set of formulae. So I'll just demonstrate to you how we can get this from this figure. Again, remember in our physics applications, it's more important to just know how to do the application rather than the whole derivation. But at the same time, just for your own knowledge, you should know the derivation. So anyway, in this figure now, let's say that if this side is x, this side is also x. Okay, so our magnitude of a plus b is 2x. Because remember, this was getting bisected. Let's say this side is y. So this side is also y. So our magnitude of a minus b is 2y. Okay. Now concentrate on this right angle triangle. You can see this is a right angle triangle. So you can see that x upon a is cos alpha. So that is cos theta by 2. Because also remember alpha is theta by 2. Okay. And beta becomes 90 minus theta by 2. So that's another important property. I'll put that up there also. So along with alpha, you also have the special formula for beta that becomes 90 minus theta by 2, where beta is the angle of the difference of the two vectors a minus b with respect to the vector a. So coming back here, this tells us that x is equal to a cos theta by 2. And similarly, y upon a, you can see, is sine alpha. Okay. So that is sine theta by 2. So y is equal to a sine theta by 2. Okay. So plug that back in over here and we get your special formula that mod of a plus b is equal to 2a cos theta by 2 and mod of a minus b is equal to 2a sine theta by 2. Okay. If magnitude of A is equal to magnitude of B. So as I said, it's more important to remember these formulae as for direct application. Okay, so let's look at an example question. Get this. So suppose two vectors A and B expressed in the same unit are such that A plus B is perpendicular to A minus B, and magnitude of A plus B is to magnitude of A minus B is 1 is to root 3, and magnitude of A is 10 units. So then find magnitude of the vector B, the angle theta between A and B, the angle alpha, or let's say, we just find out okay, and this is the angle between A and B. Okay, so this is what we're trying to do here. Okay, so now you'll again see that if you are familiar with these theorems, then it will strike you immediately that this condition given means that our vector parallelogram should have perpendicular diagonals. So the moment that happens, you recall that means the parallelogram is a rhombus. And the moment you've done that, rest is easy. So it's a rhombus means that magnitude of A is equal to magnitude of B. Alpha is equal to theta by 2. Beta is equal to 90 minus theta by 2. Okay. And that additional property that mod of A plus B is 2A cos theta by 2. Mod of A minus B is 2A sin theta by 2. So all this comes in. Okay. Now also one thing you can see here is that when you go for this property, you can see that mod of A minus B is root 3 times mod of A plus B. So that means this is the longer diagonal. This also tells you that theta must be obtuse. So anyway, we'll understand how that's happening. Okay. So let's go with the data of the question. So A plus B is perpendicular to A minus B. That immediately tells us that they are equal vectors in magnitude. Mod A is equal to mod B. Okay. And that is 10 because mod A was given to us as 10. There's another thing given. Okay. And secondly, So that means that 2a cos theta by 2 upon 2a sin theta by 2 is equal to 1 by 3. Okay, because we know that this. Okay. So that now immediately tells us that cot theta by 2 is 1 by root 3, or tan theta by 2 is root 3, which means that theta by 2 is tan inverse root 3, which we know is 60 degrees. So that tells us that, as expected, theta is an obtuse angle. So that is done now. Okay. And now we can answer each of the questions from this. So the first part wanted to calculate mod B, so that we can see that mod A is equal to mod B is equal to 10. So that's done. Okay. Second thing, we wanted to find out theta. So you can see theta is 120 degrees. So that's done. Third thing, we wanted to calculate mod of A plus B. So that we can see that here will become 2 into 10 into cos 60. So that will be 10. So that's done now. And we wanted to find out alpha. So alpha is theta by 2. So that's 60 degrees. Okay. And to really visually understand all this, we can also just draw the shape, which will give us a good sort of geometrical idea of what's happening over here. So what's happening here exactly is that we are dealing with a 120-degree rhombus with the sides of 10 each. This is our A, this is our B. So our A plus B and A minus B are like this. So this is the geometrical shape that is corresponding to all this data. Okay. Right. So these are the special properties of vector addition and subtraction via parallelogram law, which you can take care of. Okay. Now moving on to the next part of vector algebra, where we'll see how we can add or subtract multiple vectors. So addition of more than two vectors. So for this kind of situation, what we generally do is we use two options. The first method is the geometrical method, which is called the Polygon Law. And the second method is the more common one that we use. More often than not, we use the second method, which is the component algebra method. Okay. So we will discuss both of these, but just as a precursor, I'll tell you that the first method or the geometrical method will make sense for us at a practical level only in certain special cases where it is from the data of the situation we are solving, it is easy to understand that the shape we are drawing is a well-known geometrical shape. If it is not the case, then the first method is not going to be useful for us. Whereas the second method, component algebra method, is universal. We can just blindly apply it to any data that we see. Okay, there's no question of convenience versus non-convenience. That's why I said that it's more common to use the second method. Okay. So anyhow, let's see each method. So polygon law method is that if we are given a number of vectors, let's say we're given some vectors, some arbitrary vectors like this, n number of vectors are given to us, say e1, e2, e3, and like this number of vectors are given. So this is the last one. So what we do is draw these vectors, okay, head to tail, as if you are adding displacements into a shape such that they are consecutive sides of a polygon. Okay. Then the resultant of them, that is e1 plus e2 plus, you go on adding till you come to whatever last vector. This will be nothing but the vector from the origin of e1, the first vector that we added, to the tip of the last vector an. Okay, so in principle, this is what the thing is, the polygon law. Okay, and we will see next how to apply this. Let's take some examples to understand this. So what we have to do is we have to arrange all these vectors in a new diagram where we draw them head to tail instead of staggered like this. So you pick up the first vector a1, then from its head you draw the second one a2, then from its head you draw the third one a3, then from its head you draw the fourth one, whatever a4 is, a5, whatever, like this. You go on drawing these vectors, whatever they are, till you come to the last one. Suppose the last one is like this now. So e1, e2, e3, and in between I have some vectors which are just in continuation till I come to whatever last one this is. So now your resultant vector, which is the sum of all of these, will be the vector which is pointing from the origin of your first vector a1 to the tip of the arrowhead of the last one. So this one will become our resultant. And logically, you can understand this makes sense if you think of them like displacements. So you made a displacement of a1 plus a2 plus a3 plus a4 till the last one. So this is your final position, whereas this was your initial position you started from. So your resultant displacement or the net displacement is nothing but from your initial to your final position. So it becomes like this. So that is the logic of this geometrical interpretation of the addition of n number of vectors. Okay. Now, needless to say, obviously, you can add vectors only when they are of the same physical quantity and they are expressed in the same unit. So that is something understood. So now let us look at an example or two to understand the implementation of this principle. So for example, we have a set of vectors given to us. Suppose we're given some vectors like this, where this one is the vector E, and it has a magnitude of, let us say, 60. Okay. Whereas this is the vector B, which is at an angle of 30 degrees with respect to this, and its magnitude is 80. Okay, so let me just, oh sorry, its magnitude is not 80. Let me make its magnitude 40. Okay, and this is also a magnitude 40, but this is such that this angle, or rather this angle is 30. So this angle is 150 degrees. Now we want to find the resultant sum of A plus B plus C. So this is the same line of A continued here. So B is at an angle of 30 degrees with respect to A, whereas you can see C is at an angle of 150 degrees. Okay, you can see that B is at 30 degrees with respect to A and C is at 150 degrees with respect to A. Now often this is also a point of confusion among students, that why the angle between C and A is not 30 and why it is 150. This is very clear to understand that if you draw the vector A, its line of action is like this. If you draw the vector C, its line of action is like this over here. So the angle between A and C is this one, this angle. That is 150 because this angle was 30. So that's why. Anyhow, so now let us implement our vector algebra principle. So as we have discussed, what we have to do here is we have to draw a new diagram where the vectors A, B, and C are drawn head to tail. So when we make that figure, you will see we'll get something like this. This was our vector A. Now to A's head, we will draw B. And to B's head, we will draw C. I'll see that this will come out something fairly easy for us to solve because it just happens to be a symmetrical shape. Had it not been a symmetrical shape, then it may not have been so easy to solve. So my resultant in this diagram now should be this one. The resultant sum of these three vectors should be the one joining the origin of the vector A with the head of the vector C. So this should be the resultant of A plus B plus C. So I need to find out how much this one's magnitude is. I need to find out what this angle is. So just take a moment to compare the diagrams and make sure that you understand this. So what we've done is we just picked up these vectors and placed them head to tail over here. Now let's see why it is convenient to solve this. Because the geometry is presenting us with a certain degree of symmetry. So why that's happening, let's understand. That's happening because this side is equal to this side, okay, and this angle is equal to this angle. So that means when I drop this perpendicular, I'll be getting two congruent 90-degree triangles. So that means this angle will be 90, and if this side is y, then this side is also y. So within these triangles, you can see that this side is 40, this angle is 30 degrees. So you can see that y upon 40 in this triangle is equal to what? It is equal to sine 30 degrees. So that means y is equal to 20. So now once you know y is 20, we can make use of this triangle. So in this triangle, we can see that this is your resultant. This is 2y, which will become 40, and this is 60. So this angle say alpha, and this resultant can be calculated. So this will become our resultant. Okay, so this diagram is actually not that accurate. If I draw a more accurate diagram, the shape will be more something like this, which I'm drawing next. Probably be more something like this. That this angle is coming out to be nearly 34 degrees ish, and this side is coming out to be 20 root 3. So this is a more sort of accurate diagram than this. Okay, anyhow, so this is the implementation of the Polygon law of vector addition. So as you can see, it makes sense to do this only if the sides are such that there's some kind of symmetry and it's going to be easy to solve the polygon. For example, if this side had not been 40 and had been 50 or 60 or something like that, then this would be a more irregular shape. So it would not be so easy to calculate the resultant by using the formula here or by using the geometrical shape over here. But in this case, it is working out quite easy because of symmetry. So that's where the the component law comes in. The component method just makes it like a just makes it like a general sort of method which can be implemented for any set of given values. So let's come to the second method, component algebra method for addition of multiple vectors. So in this, what happens is that even if the vectors are given in component form, the first step is we express all the vectors in component form. So in general, the general three-dimensional case, say this is x1 plus second vector is like this, and so on and so forth. We have up to the nth vector. So the resultant, which is the summation of these, or you can also express it as a summation of the vectors, the index going from 1 to n. So the resultant can now just be expressed as, just add these, applying the normal principles of algebra. So you can see you'll be able to take I cap common and write this as x1 plus x2 all the x components summed up into I cap plus all the y components summed up into j cap plus all the z components summed up into k cap. So you can see that the resultant, which is summation of the vectors, ultimately becomes summation of x components into I cap, the unit vector, plus summation of all the y components into j cap, plus summation of the z components into k cap. So this becomes a sort of general formula for us. And one very important thing that you can probably immediately understand by looking at this general formula is that we can deal with a situation where the vectors are three-dimensional and need not be coplanar. That is, they need not be lying in the same plane. Whereas anything we were discussing earlier, like Polygon Law or Parallelogram Law, things like that, you're always dealing in a two-dimensional plane. So that geometrical approach, it is limited to two-dimensional plane. Okay, we'll talk more about that in a moment. But first, you can just take note of this fact over here. Okay, so let's take a couple of application examples of this. So let's look at one example where we have three displacements. A displacement E is, let us say, 10 kilometers towards east, okay, is followed by a displacement of B, which is 20 kilometers at 60 degrees north of west, and then C, which is 30 kilometers at 60 degrees south of west. So find the magnitude and direction of the resultant displacement. So you might want to pause and try out this question yourself. Okay, I will directly go to the solution to save time. So there are two approaches we can take over here. One is the standard type of approach, which is the component algebra approach, and the other is we can also make use of the geometrical approach or the polygon law kind of approach. So first of all, let us interpret these three displacements in terms of a diagram. This 60 degrees north of west and 60 degrees south of west. So let us understand these in relation to a geometrical diagram. So let us say this is the east-west axis, which we've taken as our x-axis, and the north-south axis we've taken as our y-axis. So in this particular context now, our displacements A, B, and C, how they will be looking like. So A will be a vector displacement of magnitude 10 units towards east. Okay. Whereas in the same thing now, B will look like a vector somewhere like this of longer magnitude, 20 kilometers, okay, at 60 degrees north of west. That means this will be the direction. And in the same thing now, the vector C will be looking like a displacement like this of even longer magnitude, 30 kilometers, 60 degrees south of west, like this. Okay. So just take a moment to understand this vector diagram, how we've converted the information given into this vector diagram. Then once we've got this diagram sorted out, next thing we can do is we can either apply the component method. So if we go with the component algebra method, we'll have to express each of the vectors in component form. So A is very easy. You can see it is 10 I cap in kilometers. But for B, we'll have to put in some effort. We can see that B's x component. For B's x component, you'll have to see that this angle is 120. So it will become 20 cos of 120 degrees. So that will become minus 10. And B's y component will be 20 sine of 120, which will become plus 10 root 3. So the vector B in component form will come out to be minus 10 I cap plus 10 root 3 j cap in kilometers. And similarly for the vector C, we'll have to understand it's in third quadrant. So C's components will both be negative. Okay. So for the vector C, you can see that the total angle made with the x-axis, with the positive x-axis, this angle will be 240 degrees. It will be 180 plus 60 for C, 240 degrees. Okay. So that is why C's components will become like this now, 30 cos 240 degrees, which will become minus 15. That will be the x component. And 30 sine 240 degrees, which will become minus 15. So the vector C in component form will become minus 15 I cap minus 15 root 3 j cap in kilometers. Now we can see that the resultant, which is the sum of A plus B plus C, we can now express this as the individual sum of the x components plus the individual sum of the y components. Okay, so substituting these values, you can see it is 10 minus 10 minus 15, okay, plus 0 plus 10 root 3 minus 15 root 3 j cap. So this comes out to be a vector which is minus 15 I cap, okay, minus 5 root 3 j cap. So this is what our resultant is. So to understand the resultant's magnitude, we'll just do this. Okay. So we can take 5 common. Root 3. So magnitude of the resultant is this. Now for understanding the direction, what we'll have to do is we'll have to draw this vector in our xy plane. which we have already taken such that we know that the x-axis points towards east, y-axis points towards north. Okay, so when we draw this resultant vector now here, rather this resultant vector, when we draw this should be like this. It should have this kind of a shape. This is our resultant vector. It should have an x component of -15 and a y component of -5√3. So if this angle is some alpha, we can see that tan alpha is 5√3/15, which is 1/√3, which means alpha is 30 degrees. So we can see that the direction is at 30 degrees south of west. This angle is becoming 30 degrees. So from south towards west, it is 30 degrees. Okay, so I will just take you through this once more from the component step. So once from the earlier diagram, you have got A, B, and C in component form. Once you figured out this component form, next thing is you substitute these here. Substituting all that information here, and then you're getting this. This is your resultant vector. Then if you just draw the vector, you can understand its direction. And obviously you can figure out its magnitude by using the formula. So this is a situation of how we'd add three vectors or multiple vectors in a two-dimensional plane. Then we have to just make use of xy plane. The z component is not coming into play. Okay, so let's see the next type of method we can use of solving this. So based on this particular diagram that we had got, instead of using the component algebra method, we can see if we can make use of any kind of geometrical method of solving this. So let's look at that next. So next thing we look at is how to make use of the geometrical or the polygon law type of method to solve this. So this was also 60 degrees. So as I told you that you have to remember that the geometrical method will make sense only if there is some kind of symmetry in our problem. So we see here that there is in fact some kind of symmetry. So you start by drawing the vector A, okay, then go on adding the vectors B and C to it, head to tail. So the second vector B will be drawn like this, such that this angle here, the angle between A and B, which you can see is 120 degrees. So this is 20 in length, this is 10 in length. The vector A, this is the vector B. And then when you add C next, you see that C's direction will have to be such that that also kind of makes a symmetrical kind of situation. You can see that C will be of length 30 units in all, but more importantly, it will be such that this angle between B and C, that is 120 degrees. So here this angle is also 120 degrees. Okay. And now in this particular shape, what is our resultant? Our resultant is going to be the vector from the origin of A, that is this point, to the tip of C, that is this point. So that is going to be the resultant. So now we have to figure out that can we find the magnitude of this resultant and its direction by making use of geometry. Okay, so the answer to that is going to be yes, because there is a type of symmetry that is occurring here. And let's explore that symmetry. So this is east, this is south. That symmetry you will see is occurring because this angle is 60 and this angle is 60. Okay, so if we now just do one simple thing of extending this line here, we just extend this line, see that we are able to break this polygon into an equilateral triangle. This whole triangle is equilateral, and another triangle which will come out to be isosceles. Now I'll show you why it is isosceles, because you'll see that this side will be 10 because this side is 20, and likewise this side is 20. So that means that this side is again 10. So that means that this triangle that we've got, it's an isosceles triangle. So we can make use of the geometry of the isosceles triangle. So I'll just magnify and show this again to you. Okay. So once again, what is our starting point? These two angles are 60. So therefore, if I extend this angle is 60, and I get an equilateral triangle inside. So this is an equilateral triangle. That means this side being 20. So this side has to be 20, and this total has to be 20 now. So that's why this is now 10, and because this was already 10. So now you can see that this is an isosceles triangle. So this angle will be equal to this angle. Okay. And immediately you have the sum of the sum of interior opposite angles is this. So alpha comes out to be 30 degrees. You can see the direction of R is at 30 degrees south of west, because this is west. So R is at 30 degrees south of west. That's clearly coming out. Okay. And as far as the magnitude of R is concerned, you can make use of geometry. You can drop a perpendicular here. So isosceles triangle will always bisect. The perpendicular will bisect the base, and you will get these two. So within these two triangles, you can see that x upon 10 is equal to cos alpha, which is cos 30 degrees. So x will become 10 cos 30 or 5 root 3. So magnitude of R will become 10 root 3. So both the results kind of verify what we had got by making use of the component method. But once again, you see, we had to rely on the symmetry, and if we had more random values, then that symmetry would not have been there. So this method would not have been feasible, whereas the component algebra method is always feasible. So that is something very important to understand in this kind of situation. All right, now next up, we will look at a situation where there's a bit of three-dimensional kind of application. And since we are doing this as a revision of vectors in context of physics, so we'll take a type of physics type of problem to understand. The next example to wind up this section where we are doing addition of vectors. So now let's say we have a situation like this. We have an inclined plane. Let's say we have a smooth inclined plane, which I'm drawing three-dimensionally like this. So this is, and this surface is a smooth inclined plane in which I have kept a particle. This is the horizontal. This is the vertical. So this is the three-dimensional view of a smooth inclined plane. Let's say at theta equal to 37 degrees with respect to the horizontal. Now a particle of mass m equal to, let us say, 10 kilograms and charge plus q is placed on the inclined surface. Due to an external field, due to an external electric field, which is something we'll learn about later, so don't worry about it right now. The particle P experiences an electrostatic force F of magnitude, let us say 60 newtons, horizontally along the inclined surface. So I will show that in the diagram here. So the electrostatic force that the particle is experiencing, it is a horizontal force, but it is along the inclined plane, tangential to the inclined plane. So that will be a force like this. This is the electrostatic force. Okay. In fact, let's give it the subscript of E. Okay. As shown. So now next thing is this particle is being held at rest by the action of another external force. So this particle is held at rest by some external force. Okay. So you want to find the magnitude of this external force. So just take a moment to go through the question and I'll explain. Okay, so I'm sure you have gone through the data in this question. So you will first of all have to understand that because this is a three-dimensional case, we'll have to make use of three-dimensional system of axes. And most likely that system of axes will be convenient if we take one of our axes. So I'm just superimposing the system of axes over here. Okay. So if we take the horizontal plane to be our xy plane. Okay, so let us say we take this direction as our x-axis, the direction in which the force is acting. This is our x-axis. The direction in which gravity is, I mean the vertical direction, let's take that to be our Z axis, because so this is the vertical direction, and therefore this direction here, which is basically going into the plane normally, this will become our y-axis. So the xy plane is the horizontal plane. So we will now understand this in two-dimensional diagrams. So let us look at the same diagram first. The two-dimensional diagram in the YZ plane. If you compare the above diagram with the situation of the YZ plane, you will see that we will be seeing the inclined plane from the side in this diagram. You will see the inclined plane is making an angle of 37 degrees with the horizontal from the side, because we have drawn our y and z axis to be like this. So this is our vertical axis, and xy plane was horizontal. So that is what it will look like. So in this view now, what are the forces we will be seeing on the body? Let's understand that. So on the body, we'll be seeing the gravitational force, and the normal contact force which the surface will be applying. So we'll see the weight of the body. So that will come out to be now, that's in the negative z direction. So when we write it in vector algebra, if we are taken the mass to be 10 kilograms, and we'll take acceleration due to gravity to be 10 meters per second square. So acceleration due to gravity is a vector which is pointing vertically downwards like this now. So this will be 100 in the negative k cap direction in newtons. Okay. Whereas normal reaction will be some vector n, which we don't know as of now, let's say, but its direction you can see, we can figure out. So how we can figure out the direction of normal reaction? By understanding this geometry here. This angle is theta, so this angle will be theta. So when we break the normal reaction into components, you can see that the normal reaction with respect to yz, this angle here is theta. So it is some n cos theta, it become 4 by 5n, because theta is 37 degrees, and this is n sine theta, so it become 3 by 5n. So when we write this in component form, you can see that the y component will be minus 3 by 5n j cap, and the z component will be plus 4 by 5n k cap. Okay. Now we can also understand here that if you break the weight into components, like this angle will be 37. So this component of weight will become mg cos 37, or 4 by 5 mg, or in this case 80 newtons. Okay. And this component of weight will be mg sin theta. So in this case it will be mg sin 37, or 60 newtons. Okay. So you can also understand from this that the magnitude of the normal reaction, because it is the normal reaction is basically coming because of the pressing force of mg against the inclined surface. So the magnitude of normal reaction will be equal to mg cos 37. That is, it is the component of the weight into the inclined plane, okay, into the inclined surface. So from that, now we will know normal reaction as a vector quantity, both components in newtons. Okay, so we can see that the normal reaction will have a magnitude of 80 newtons. Okay. So we know this, and we know the normal reaction in component form. So from this, now we will know that the normal reaction is minus 48 I cap plus 64, sorry, minus 48 J cap plus 64 K cap. In newtons. So this is our normal reaction in newtons. So far we know these two forces. We know mg, we know normal reaction. Now what else is acting on the body? There is also electrostatic force, which we are not able to see in this diagram. Okay, so note that in this diagram there is also electrostatic force that is along the x-axis, okay, which you can't see in this diagram, but you can see in the earlier diagram. Electrostatic force is acting along the x-axis, like this. So if you see the top view now, so now if you look at the diagram looking into the x-axis, or rather looking into the xy plane, so this is the 2D view in the xy plane. So in that plane, the force acting on the electrostatic force acting on the particle, you'll be able to understand, is like this. There's an electrostatic force which we said was of magnitude 60 newtons. So the electrostatic force in component form we can write as 60 I cap in newtons. So this is the third force acting on the body. Okay. So now in all we can see that there are three forces. Weight, which we saw, is minus 100 K cap in newtons. Normal reaction, which we saw, was that minus 64 J cap plus 48 K cap in newtons. Okay. And now the electrostatic force, which we are seeing, is 60 I cap in newtons. Okay. So what has to happen is to keep the body at rest. So to keep the particle at rest, to hold it at rest, some external force has to be applied. Somebody has to hold it by application of a force such that the net force on that has to become zero. Okay. So the resultant of external force plus the weight plus the normal reaction plus the electrostatic force which is acting, this has to be zero. So in other words, the external force has to be equal to negative of the resultant of these three forces. Okay. So next step is, from this we will calculate the resultant of these three forces, mg plus n plus electrostatic force. The resultant of these three forces we can see will become how much. So just add all this. So along the x-axis you can see there is only 60. Along the y-axis you can see there's only minus 64. And along the z-axis you can see there's minus 100 plus 48. So that is how much now? That is 52. So this will become minus of this thing. In newtons. Just substitute this. Okay. So from that we come to the conclusion finally that our external force is 60 I cap plus 64 j cap, rather minus 60 I cap, my mistake, plus 64 j cap minus 52 k cap in newtons. This is the amount of external force, and so the magnitude of that will just become square root of 60 square plus 64 square plus 52 square, which will be roughly, if you do a calculation. So if we do a sort of rough calculation of this will come out to be square root of 10,148, which will be nearly 100.74. Okay, so you can say that it's nearly 101 newtons, something like that. So this will be the magnitude of the external force. Okay. So you can see this is quite a massive calculation we have done, but because it's three-dimensional as well as we are dealing with different type of forces. But this is the full scope of vector algebra in context of addition or subtraction of vectors. How we can apply it in a complex type of physics problem. So if we have that situation where our forces are not in a two-dimensional plane, they are three-dimensional, because here there's a vertical force of mg, there's a normal reaction which is acting sort of diagonally in the vertical plane, and then there's the electrostatic force which is again horizontal but perpendicular to the weight, because it's tangential to the surface. So it's a three-dimensional situation, so we are having to deal with that. So this is where the full scope of component algebra in three dimensions comes in. Okay, so that brings our second session here to a close today. So hope you have enjoyed and learned a little bit from the session. Okay. As I told you that if you are a little less familiar with the basics of vectors, then please do brush up the basic concepts from your standard textbooks or reference books, whether that is your NCRT or any other source, any specific source for JEE or engineering entrance type of books, etc. You can use any source, you'll get the basics. It's not too difficult. Then you can come back to some of these questions and you'll understand them better. So just a heads up about the next lecture, what we'll be learning about. We'll be learning about the dot product of vectors, or what we call the scalar products, this type of operation, which is used a lot in physics for calculation of things like work done, etc. And then we'll be learning about the cross product, which is again very important in physics, because through the cross product we will learn to work out things like moment of force, or later in class 12 you will see the magnetic force acting on a charged particle. That also depends on cross product of velocity and magnetic field. So two very crucial vector operations from the point of view of physics. So we will learn to deal with these in the next lecture, and then we'll move on to some of the aspects of basic calculus like differentiation and integration. So that's it for today's session, people. Wish you all the best and hope you have enjoyed the session.